Welcome to the course Business Analytics and Text Mining Modeling using Python. So, in previous few lectures we have been discussing the aspects of working with data, and specifically we stopped at this point. We wanted to discuss the binning of continuous variables. So, we will pick up from this point itself. So, as you might understand that many two types of variables, continuous and categorical variables, like we have discussed in our previous courses, business analytics and data mining modeling using R. So, in many times we are required to perform binning of continuous variable. That means we are required to transform continuous variable into a categorical variable. So, for that we will have to create categories, we will have to create bins. That means those category and those groups, we also refer those groups as bins. So, we will have to perform all that. So, how do we complete that process and automate that process using in Python? So, for that we have few examples here. So, let us talk about this variable age. So, let us say we have these ages of certain points, certain individuals. So, this is a list of these values. So, let me create this variable here ages, and let us say we want bin lengths of these bins of this interval, let us say 18 to 25, then 26 to 35 etc, so on. So, we can specify the bin edges here. So, for example, first bin is starting 18 and ending 25. So, we can note down these end points here and specify that in a variable, let us say bins, and this is these edges are going to be used to create these groups or categories or bins. So, let us define the bins as well. So, if you focus on the bins that we just defined 18, 25, then 35. So, depending on the bin lengths that we actually wanted. So, based on those bin lengths we can define these bin edges, and then these bin edges are going to be used to cut the variable, the continuous variable, into appropriate bins. So, once we do this, ages variable can be called age underscore groups variable. So, for this to perform this process we use cut function. So, this is a pandas function pd dot cut, and first argument we are passing the variable ages, the continuous variable which we want to cut, where we want to perform binning, and then we also specify our bins, that means bin edges which we would like to follow to actually perform the binning on the first argument for the variable ages here. So, if I run this, we will end up with we will have the binning here. So, if you look at this, the ages variable that we had 12 values there, and in the output 232. If you look at the first value, which was actually 20, has now been replaced with it's a bin which is starting from 18 to 25. So, that group, and similarly 22 also is also falling in the same group. So, the same bin there. Similarly for 25. Now, 27, this will change. So, you can see the change in the category 25 to 35, then again 21 in the first group, 18 to 25. So, in this fashion all the 12 values they have been put into their appropriate bins as per our specified bin edges, as per our desired bin lengths. So, finally we are end up with the 4 intervals. So, when we specified 5 bin edges, so essentially we will have 4 groups there. So, you can see those categories are also specified, and 18, 25, then 25 to 35, 35 to 60, 60 to 100. So, if you look at this age underscore group, so this has become a categorical variable rather an ordinal variable, because as you can see in the category the order is important. One group is lower than the other one category can be considered as lower in comparison to other categories. So, this is the ordinal variable. The age has been we have been able to convert age into an ordinal age underscore groups variable. So, in the analytics sometimes we are required to perform this kind of data transformation. Now, if you want to have a look at a nicer presentation of age underscore groups. So, for that we have quotes attribute. So, in this quotes attribute, instead of mentioning the bin interval, we can have the numeric codes to represent those those bins. So, instead of 18, 25, 25, 35, 35, 60, 60, 100, we can have 0, 1, 2, 3 to represent those intervals there, those categories. So, if I run age underscore groups dot codes, we will have 12 values with these numeric codes in this form. Similarly, we also have another attribute categories, which will again just inform us about the intervals that we have. So, if I run this, we will have all the categories of the that are there in age underscore groups, as you can see. Now, we can also compute frequencies for different categories, different bins of age groups. So, for that we can call this pandas function value underscore counts, and we can pass on this variable age underscore groups. So, if I run this, we will have in the, as you can see in output 235 for each of the interval, for each of the bins or categories that we have created. We have the frequency number. So, 18 to 25, 5 instances of this particular category, second one 35 to 60, 3 instances, 25 to 35 3 instances, and 60 to 100 1 instances. So, in this fashion we can compute the frequencies. So, this is similar to this data is similar to what we typically observe in a histogram. So, this is how we can actually perform this. Now, if we look at the intervals, the way they were created, the bin intervals, the open close sides, if we want to change that, we would like to if you look at the default thing, the starting the starting side is the open parenthesis, that means open side, and the closing side is the brackets, that means closed side. So, that means inclusive side also. So, if you want to change this interval sides and how, whether they are going to be open or closed, so that can also be done. So, by default left side is open and right side is closed. So, we can use right argument in this cut function to specify this. So, the next line of code, you can see that pd dot cut, we are going to do cut. Now, in this case we are using ages, and those bins also, bin edges also, and right argument it is indicated as false. So, therefore, now right will be closed side here, and the other side would be reversed. So, if I run this, you can see the bin intervals the way they have been defined, that is actually has been changed. We can also change bin names. So, instead of using these values to indicate the interval, we can have slightly qualitative terms to actually define these intervals. So, for example, 18 to 26 we can call this age group as youth, 26 to 36 we can call this age group as young adult, 36 to 61 we can call this age group as middle aged, and then 61 to 100 we can call this senior group. So, this is the qualitative term for defining these intervals, which are right now using numeric values. So, for this we can use the labels argument in the cut function. So, whenever we are creating these bins using pd dot cut, we can use this labels argument and specify this. So, if I run this one, so you can see all the 12 values that we had in the ages variable, now it has been converted into, let us say, age underscore groups kind of variable, and the values, now the qualitative terms, the linguistic terms are being used here, youth for those values, young adult, and in this fashion. Now, if you look at the categories also, so these labels are being used now instead of the intervals with the numeric values. So, youth less than young adult, less than middle age, less than senior. So, in this fashion we would be able to create the binning and rename them using linguistic or qualitative terms as well. Now, we can also create, we just if we do not want to specify the bin length or bin edges, we can just specify the number of bins that we want. So, if we just specify the number of bins, so equal length bins are going to be created. This can also be achieved using same cut function. So let us take an example here. So now we will use this wire2, we will take random values following uniform distribution. So wire2, and what we will do, we will create 4 bins. So in the pd dot cut function we will pass that value 4 to indicate that we want 4 bins. So it will create equal length bins for us. And third argument, if you look at precision, that is just to indicate the decimal points that we want in our output. So if I run this, we will have different bins, and these are equal sized bins. So you can look, you can have a look at this 0.18 to 0.38. If you look at the categories, so we have 4 categories here, then 0.38 to 0.58, 0.58 to 0.7, 0.78 to 0.98. So you can look at the length of these bin interval, that is equal here, and appropriately the age values of the age variable, they have been classified with one of these categories. Now bin lengths can also be based on sample quantiles. So there also, even if we apply sample quantiles, we are going to typically will or roughly will get equal length bins. So for that we have another function, q cut function, which is going to use these quantiles. So let us take this example for this variable that we had just created, wire2. So wire underscore groups, so this is the categorical variable we can create using pd dot q cut function. First argument we are specifying the variable, and then second one the number of groupings that we want, number of bins that we want. So let me run this, and you can see that if you look at the categories and the specific values, slight change from the previous output through 39. You can compare the categories in 239 and 240. There we had 0.18 to 0.38, now we have 0.182 to 0.331, and similarly for others also. So you can see here. So slight of course slight changes in terms of bin length. However, if you look at the frequencies for bins here, so that is the advantage here using the sample quantiles here. So if I run pd dot value underscore counts here, so you can look at the frequencies. So frequencies are same in each of these groups that are based on sample quantiles. You can see 5 values in each of these groups. Now we can also specify our own quantiles. So we can use the same function pd dot q cut, and in the second argument, instead of asking for a number of bins, for example in 240 we specified we wanted 4 bins using sample quantile, we can specify the quantiles itself using a list. So you can see 0, 0.25, 0.5, 0.75 and 1. So 5 values we have specified. So essentially we are looking for 4 bins using these sample quantiles. So if I run this, and you can have a look at the output. You can also compare the output 240 and 241. If you look at both the outputs are same. So essentially when we called when we asked for 4 bins using the pd dot q cut function and did not specify the actual quantile, it was taking these quantiles itself. These 0 to 0.25, 0.5, 0.75. So these quantiles are by default taken if we do not specify the quantiles in the q cut function. So if you want different quantiles, you can always go ahead and specify the same. So this was about binning of continuous variables and different variations, different approaches that we can take to perform these binnings and transformation that we talked about. Now let us move to the next aspect. Now this is about finding outliers. So outlier detection and replacement is an important task in the analytics domain. So to demonstrate this, let us take this example here. In this case we have 1000 cross 4 1000 cross 4 array with these dimensions. So let me define this. I can. So typically when we are when we are analyzing outliers, typically we like to have a look at the descriptive statistics. So in this case, for this data frame DF11, we will like to call this method describe, and we will have a number of multiple statistics here. So you can have a look here, count, mean, standard deviation, mean, 25 percentile, 50%, 75% and max. So you can have a look at these multiple statistics, and these statistics will in a way indicate can indicate the presence of any outliers there. So higher higher max value and a lower mean might indicate that there are outliers. So for example, if we have a look at the mean values at different columns, so they are in the range of, let us say, 0.049, 0.003, and if you look at the max value in these columns, so those values are going in the range of 2.98, 2.74, 3.05 and 3.45. Similarly, min values also, they are going in the negative direction, minus 3.57, minus this. All of them are in the absolute sense they are above 3. So you can see that mean is quite low and min and max value are on the higher side. So there are chances that outliers are present in this particular data set. So how do we find out these values which are exceeding, let us say, 3 or minus 3. So let us find out values which are exceeding 3 or minus 3 for a particular column. So as you can look at the mean statistics for all the columns, there are values which are exceeding which are actually exceeding 3 in the absolute sense. So let us pick the column with the index 2, column 2, that is third column. So what we will do, DF11, and we will specify the index to pick that column, and within the brackets now we are taking an absolute of this particular column's values and then comparing it with 3. So for any values where the value is greater than 3, so those rows are going to be defined as true, and those would be selected. So if I run this, you can have a look at the output 245. So we have got two rows, 298 and 751 with row index 298 and 751, and both of them are from the column 2 and having values more than their absolute value is more than 3. You can see minus 3.06 and 3.05. So in this fashion we can filter out these outliers. Now we can apply the same thing for all the columns. So you can see here DF11 absolute value dot any1. So we are specifying the axis and we can run it here, and you can see that. So you can find out here again from the output. So all the rows where we have at least some value with greater than 3. So exceeding 3 or minus 3. So you can see 60. So all these row indices are there in the output, as you can see here. So total we have 13 such rows where this is happening in one or more columns. Now let us move to another aspect here. So one thing is to find out these outlier, and then sometimes we would like to change the values also depending on our modeling requirement. So for a given range we can modify value. So let us say if there are any values which are outside the range of minus 3 to 3. So we would like to replace them with all those values as either minus 3 or 3 depending on the sign. So we can record the sign using the sign function, and then we can replace the value with either 3 or so we can replace the value with 3, and the sign will record using np.sign function here. So the next line here we are actually performing that thing. So we are first in the identifying in the left hand side all the rows like the previous output where where the values are greater than 3, and then you can look at right hand side, we are recording the sign for those, and then multiplying it with the 3 value. So, if I run this and let us have a look at the describe method output here again. So, you can see that minimum value, minimum statistics for all the columns and max statistics for all the column. Now, it is within -3 and 3. So, in this fashion what we have actually done, we have replaced all the outlier values, values which were exceeding 3 or -3 with actually those numbers -3 and 3 itself. Now, let us move to another aspect which is about random sampling or random reordering of rows. So, this is also very important because we typically will be dealing with larger data sets and therefore, we would be drawing a sample points from there. So, typically we do random sampling. So, how do we perform this in the Python Python platform? So, let us take the example of this data frame. So, this data frame we have 5000 rows and 4 columns. So, let me first create this one. So, you can have a look 5000 rows 4 columns here. Now, first thing that we will like to demonstrate is randomly sampling n rows without replacement. So, this is the more common exercise, more typical exercise in modeling context where we randomly draw sample points, randomly draw cases. So, let us say n rows without replacement. So, for this we can use sample method and let us say we would like to draw 500 rows out of 5000 rows that we have in our data set. So, for this we can apply this we can call this method sample df12.sample and we can specify in the keyword argument n the number of points that we would like to sample 500 in this case. So, if I run this and you can have a look at the output 250. So, if you focus on the row indices here, these values have been randomly, these indices have been randomly drawn from 5000 rows that we have. So, you can see the random index values are starting like 1180, 3329, 2319, 3968. So, all these seem to be quite random and so therefore, the sample method is able to provide us those rows. Now, sometimes we would like to we would like to draw these cases with replacement. So, for that we have this replacement argument. So, we can specify replace as true. So, again same method df12.sample n is equal to 500 and replace true. So, in this fashion if I call this method, you would see the output is going to be based on that process. So, again you can see because this is also a random sampling here different row index values we can see in the output as you can see in 251. Now, let us move forward to the next aspect which is about random reordering of row indices. So, if we want to certain situation we would like to perform this also. So, for that we have this permutation function. To demonstrate this we will take this define this data frame df13 and we have 5 rows and 4 columns in this data frame and what we can do is we can if we want to perform a random permutation we can call this np.random.permutation and we can specify we can specify the number of rows there. So, we have 5 rows. So, if I run this we will have the randomly drawn reorder for these row indices. So, if you look at the output 253 now 3 is coming first, then 4, then 0, then 1 and 2. Now, I can use the reindex method here to actually use this random permutation here. So, I can call df13.reindex and I can pass on this random permutation that we have just drawn and I can run this and you can see now you can focus on the output 254 and specifically the row indices. So, you can see 3, 4, 0, 1, 2. So, those random permutation of random reordering of rows have actually been executed. Instead of reindex method we can also use the take method here. So, df13.take we can pass the permute and we will get the same output. So, let us move forward. Now, next thing is about dummy variables. So, as you would understand that in the analytics context, we would be dealing with categorical variables, and typically in most of the softwares, most of the software, most of the implementations of algorithm, whether statistical or data mining, typically categorical variable they are converted into dummy variable. And so how do we perform this process? So, dummy variable, this is about converting, as you can see in the comments, converting categorical variables into dummy variables. So, what are dummy variables? They are going to be filled with ones and zeros. So, ones will indicate the presence of that category in a row or observation or case, and zeros will indicate the absence of that category in a row or case in a particular observation. So, given a categorical variable and it might be having values like, if there are 4 categories. So, those categories might have numeric codes like 0, 1, 2, 3. So, therefore, that particular column for that categorical variable might be filled with these values 0, 1, 2, 3, for different observation, different value. Now, we would like to convert such a column into dummy variables, where for each category we will have a separate different dummy variable, and in each of those dummy variable the values would be either 0 or 1. 1 would indicate the presence of that particular category for that row, and 0 will indicate the absence. So, that is the kind of transformation that we are required to perform in dummy coding. So, let us take a categorical variable with k distinct values, that that means categories corresponding to categories. So, we will take this data frame here. So, if you look at here, we have this one column with variable, and it has 3 distinct values A, B, C, and we have 6 rows. So, we can use get underscore dummies function, which will actually perform this dummy coding for us. So, 3 distinct values as I talked about A, B, C. So, I can call pd dot get underscore dummies, and I can pass on df14 and the column name var here. So, for this column we will have the dummy variables here. So, you can see now in the output 257 3 columns with the name A, B, C, and you can see only zeros and ones. You can compare this particular output with the previous output with the column variable column. So, you can see for B for column A in the row when we have B. So, that means for that row B category is there. So, that means A is absent. So, that is why 0 and 0. So, or in other way you can map it like this, for column A wherever 1 is present, that means in the column variable A would be indicated. So, you can check it back with the var column. So, you will get the idea about what we are trying to do here. Now, while we are creating these dummy variables, we would like to sometimes we would like to rename them as well, and in this renaming most times, more often, the typical practice is that we would like to prefix these dummy variables with the variables name. So, for that we have this prefix argument in the get underscore dummies function. So, we can use that. So, pd dot get underscore dummies df14 this variable, and we can prefix var here. So, if I run this, you can see in the output 258, and you can focus on the column names here. So, they have been changed from A to var underscore A, B to var underscore B, and C has been changed to var underscore C. Now, we can combine dummy creation and binning process. So, binning is about converting a continuous variable into categorical variable, but eventually when you convert it into a categorical variable, you will also be doing dummy coding. So, why not combine these two processes? So, we can use a combination of get underscore dummies and cut function and perform this. So, let us take this variable 3, and these are the values, and let us take this binning for this variable, these bin edges, and if we perform the binning on this variable 3 using these bins, let us have a look at the output. So, you can see pd dot cut output 262, you can see how this binning has worked. Now, let us combine. So, if you look at how we are combining this, so we are calling pd dot get underscore dummies function, because this is the later process. So, within this we are passing the PD dot cut, because this will give us the categorical variable. So, essentially categorical variable is input for the get underscore dummies variable to produce the dummies. So, the PD dot cut output of that particular function is going to be the argument for get underscore dummies in this case. So, if I run in this fashion, you can see the column that we have just got in the output, that you can see focus on the column names 0, 0.2, 0.2 to 4, 0.4. So, you can see all those bin edges that we had, they have been bin intervals have been created, and those are being used as the column names. And the dummy coding has also happened for each of these column names. We are filling with zeros and ones, so indicating the presence or absence. So, in this fashion we can in one go we would be able to convert the categorical variable into a continuous variable into a categorical variable, and also transform the categorical variable into multiple dummy variables. So, we will stop here, and in the next lecture we will start our discussion on another important aspects, especially in the context of this particular course, that is string and text processing. So, let us stop here. Thank you.